Hello and welcome to this video. In this video, we will solve problem number 51 to 60. So this is the sixth set on miscellaneous problems on AP, GP and HP. So without further ado, let's get started. But before starting, I will say what I always say, that when I'm reading the problem, you should pause the video and then you should try to solve the problem yourself. If you cannot solve the problem yourself, only then look at the solution. So let's get started. Problem number 51 says that if integration of cos to the power nx cos nx dx with limit 0 to pi by 2, then prove that I1, I2, I3 are in GP. So when you want to prove things are in GP, you prove ratio of two terms to be constant. If you can prove that ratio of two terms is a constant, then the series would be in GP. So you take two general terms, in, in plus 1. So in would be cos nx, cos to the power nx, cos nx dx. And in plus 1 would be cos to the power n plus 1x cos n plus 1x dx. Now you can expand cos n plus 1x dx as cos x cos n plus 1x dx. Now we know that cos nx is equal to cos n plus 1 minus 1 into x, which is equal to cos n plus 1x cos x plus sin n plus 1x sin x. Now this has come from trigonometry. So by observing this, we can write that cos n plus 1x cos x, that is this term we are trying to figure out, is equal to cos nx minus sin n plus 1x dx into sin x. So we substitute the value of cos n plus 1x cos nx in this one, that is in plus 1. So it becomes cos to the power nx cos nx minus sin n plus 1x sin x dx. Now if you see this part, that is cos to the power nx cos nx, is nothing but in. So we substitute in for that. And then what remains is minus cos to the power nx sin n plus 1 x dx. So this you integrate by parts, and when you integrate by parts, you will have this term which will be 0, and you will have this term which is nothing but in plus 1. So in plus 1 is equal to in plus, in plus 1 is equal to in minus in plus 1. So you take it to left hand side, it becomes 2 in plus 1 is equal to in. That is in plus 1 by in is equal to half, which is constant. And that's why we can say that I1, I2, I3 and so on are in GP. Problem 52 says that let in is equal to the integration of sin 2n minus 1x by sin x with limit 0 to pi. Then we have to show that I1, I2, I3 are in AP as well as in GP. So we figure out in plus 1 minus in, and that is equal to in plus 1. So 2 in, let's go in stepwise. I don't want to skip this. So n plus 1 minus in is equal to sin 2n plus 1x minus sin 2n minus 1x, and this dx should be here. Okay, this is badly typed. So there will be sin x over here, and then dx would be here. Now if you observe this here, then it would be 2 cos 2nx sin x by sin x dx. Sin x will get cancelled, you will have cos 2nx dx. Now if you integrate this, it will be 0 if you apply the limits. So we can say that n plus 1 minus in is equal to 0, that is n plus 1 is equal to in. Now if you integrate for I1, it is pi. So since I1 is pi and in plus 1 is equal to in, I2 is pi. So all the values will be pi. And that's why we can say that I1, I2, I3 are in AP as well as in GP. Prove that three successive terms of a GP will form sides of a triangle if the common ratio R satisfies the inequality. That is square root of 5 minus 1 by 2 less than R less than square root of 5 plus 1 by 2. So we let the sides of a triangle to be AR, AR square. Now if R is 1, then the triangle formed will be equilateral triangle. If R is greater than 1, the triangle will be formed if sum of two small sides is greater than the larger side. So we obtain R less than 1 plus square root of 5 by 2. Now if R is less than 1, then triangles will be formed if R greater than 1 minus square root of 5 by 2. You can proceed similarly in the example, and then the range is what we need. Find out whether 111 up to 91 digits is a prime number. So we write 111 as 10 to the power 90 plus 10 to the power 89 and so on, which is equal to 10 to the power 91 by 10 minus 1. Now we know that 91 is equal to 13 into 7. So we multiply or divide by 10 to the power 13 minus 1 or 10 to the power 7 minus 1. So we can rewrite 10 to the power 91 minus 1 as this should be minus 1 here. There should be a minus 1 here. 10 to the power 91 minus 10 minus 1 is equal to 10 to the power 91 minus 1 minus 1 is equal to 10 to the power 91 minus 10 minus 1 minus 1 is equal to 10 to the power 91 minus 10 minus 1 is equal to 10 to the power 91 minus 10 minus 1 is equal to 10 to the power 91 minus 10 minus 1 is equal to 10 to the power 91 minus 10 minus 1 is equal to 10 to the power 91 minus 10 minus 1 is equal to 10 to the power 91 minus 10 minus 1 is equal to 10 to the power 91 minus 10 minus 1 is equal to 10 to the power 91 minus 10 minus 1 is equal to 10 to the power 91 minus 10 minus 1 is equal to 10 to the power 91 minus 10 minus 1 is equal to 10 to the power 91 minus 10 minus 1 is equal to 10 to the power 91 minus 10 minus 1 is equal to 10 to the 10 to the power 91 minus 1, there should be a minus 1 here, there should be a minus 1 here. It's all bad typo. Now we divide this by 10 to the power 7 minus 1 and multiply with 10 to the power 7 minus 1. So it would be 10 to the power 84 plus 10 to the power 77 plus 10 to the power 70, and this would be 10 to the power 6 plus 10 to the power 7, 10 to the power 5, and so on. So see that this is an integer, therefore given number is not a prime number. Problem number 55 says that find the natural number a for which sum of fak, where k varies from 1 to n, is equal to 16 into 2 to the power n minus 1, where the function f satisfied the relation fx plus y is equal to fx fy for all natural numbers xy, and further f1 is equal to 2. Now we know that fa plus k is equal to fa fk, because fx plus y is equal to fx fy, so we take the sigma. So fa would be outside, and we have the sum of f1 plus f2 up to fk. Now f2 is equal to f1 plus f1, that is 2 square. F3 is f1 into f2, that is 2 cube, and so on. So we have the sum, that is 2 to the power a on the left side, because fa would be 2 to the power a. 2 plus 2 square up to 2n is equal to 16 into 2 to the power n minus 1. We solve this, we arrive at a is equal to 3. Problem number 56 says that in a certain test there are n questions. In this test, 2 to the power n minus 1 students give wrong answer to at least I questions. If total number of wrong answers given is 2047, find the value of n. So number of students giving wrong answers to at least I questions is 2 to the power n minus I. So number of students giving, there is a typo here, giving wrong answers to at least I plus 1 questions would be 2 to the power n minus I minus 1. So number of students giving wrong answer to exactly I questions. So you see, number of students which gave wrong answer to at least I plus 1 question is this, and at least I questions is this. So if we subtract this from this, we will get exactly I questions having wrong answers. So we get 2 to the power n minus I minus 2 to the power n minus I minus 1 as that number, that is, these many students have given wrong answer to exactly I questions. So also we find that number of students giving wrong answer to exactly n questions would be 2 to the power n minus 1 minus n, that is 1. Now total number of wrong answer, we take the sum of the series 2 to the power n minus 1 minus 2 to the power n minus 2. This would be multiplied with 1, because those many students gave wrong answer to 1 question. Number of students giving wrong answer to 2 questions would be 2 into 2 to the power n minus 2 minus 2 to the power n minus 3, and so on. Now once we have found this series, it is only a matter of summing it, which is equal to 2047 is equal to 2 to the power n minus 1, which gives us n is equal to 11. Problem number 57 says that if S1, S2, S3 up to S2n are the sums of infinite geometric series whose first terms are respectively 1 to 3 up to 2n, and common ratios are respectively 1 by 2, 1 by 3 up to 1 by 2n plus 1, find the value of S1 square plus S2 square plus S2n minus 1 whole S2n minus 1 square. So S1 is 1 by 1 minus 1 by 2, that is 2. S2 is 2 by 1 minus 3 is equal to 3. S3 is equal to 3 by 1 minus 1 by 4 is equal to 4, and so on. So sum would be 1 square plus 2 square plus 3 square to 2n square minus, hang on, this would be 2n minus 1 whole square actually. Okay, no, not that, it won't be, it will go up to 2n whole square. Okay, this should be whole square, that is 4n square. All right, and minus 1 would, hang on, I'm confused now. Let me read the problem. So we have 2n and infinite geometric series up to 2n. We have two common ratios, this much. Okay, so this should be minus 1 should be here as separate minus 1. This is s2n square minus 1. It is not the subscript of s2n. So we have 2n whole square minus 1. Here 2n whole square minus 1. This is s2n square minus 1. So minus 1 is here, and here we have the product. So it was a very simple problem actually. Problem 58 says that a square is given, a second square is made by joining the middle points of the first square, then a third square is made by joining the middle points of the sides of second square, and so on till infinity. Show that the area of first square is equal to sum of areas of the succeeding square. So we take this square ABCD, we take PQRS the midpoints. So we find that AC is equal to square root of 2A if side of the square is A, if each side of the square is A. So in this case, PQ would be AC by 2, okay, that is A by root 2. The question is how PQ is AC by 2. So that is very simple to prove. You see angle ABC and triangle ABC, and you see triangle PBQ. Okay, so you look at the sides here. This angle B would be common in both the triangles. Now this is QB is half of BC, PA is half of AB. So so we find that the triangles would be common, sorry, similar. Okay, because one angle is common and two ratios are equal. Two sides ratio are equal. So these two triangles ABC and PBQ would be similar triangles, and that's why the ratio of PQ with the AC would be half, because the ratio of other sides is half. So we get PQ as A by root 2. So once PQ is A by root 2, the sum of second square would be A square by 2. And once you join the midpoints of PQRS, the area of third square will be equal to A square by 4. The sum of all squares except the first one would be A square by 2 plus A square by 4 up to infinity, which is equal to A square, and thus we have proven the required condition. Problem 59 says that if A is the value of x for which function 7 plus 2x log 25 minus 5 to the power x minus 1 minus 5 to the power 2 minus x has the greatest value, and r is equal to limit x tends to 0, integration of t square by x square tan pi plus x dt with limit 0 to x, find the limit n tending to infinity, sum of ar to the power n minus 1 with limit n is equal to 1 to n. So here we are given one function fx, which is equal to 7 plus 2x log 25 minus 5 to the power x minus 1 minus 5 to the power 2 minus x. So we differentiate it. We get after rearrangement the function f prime x is equal to log 5 by 5x 5 to the power x plus 1 into 5 to the power x minus 25 multiplied with 5 to the power x plus 5. Now this fraction and 5x plus 5, that is log 5 by 5x to the power x plus 1 multiplied with 5x plus 5 will be greater than 0 for all real x which are greater than 0. Now f prime x can be less than 0 if this term, that is 5 to the power x minus 25, is less than 0. Now this can be less than 0 if x is less than 2. Sorry, yeah, if x is greater than 2, then this would be greater than 0. It is, the conditions are not written properly. So f prime x can be less than 0 if x is less than 2, and it will be greater than 0 if x is greater than 2. Yeah. So fx has one local maxima at x is equal to 2, and it has no local minima. So the greatest value will be at x is equal to 2, that is a is equal to 2. Okay, because a is the value of x in this function. So since x has the value 2, a has the value 2. Now we take the limit here, and since the bottom side, that is the denominator, does not have a term involving t, the integration will only apply to the numerator, which is equal to x cube. Now once we have x cube here, and 1 by 3 will come because of that, we apply the limit here. This would be x square will get cancelled, x will be in the numerator, so 1 by 3, x by 3 tan x, which is equal to 1 by 3. Once we have this limit, we have our r. So once we have r and once we have a, we apply the sum formula, and n is tending to infinity, so it is sum of a gp, which is equal to a by 1 minus r, and a is 3, a is 2, and r is 1 by 3, so we substitute 2 by 1 minus 1 by 3, which is equal to 3. Problem number 60 says that if pth, qth, rth term of a gp are positive numbers abc respectively, show that the vectors log a in with vector I log a, vector j log b, vector k log c, and q minus r vector I, r minus p vector j, and vector k p minus q are perpendicular. Now we let x to be the first term and y to be the common ratio of gp. Then we have a is equal to xy to the power p minus 1, b is equal to xy to the power q minus 1, c is equal to xy to the power r minus 1. So we have log a is equal to log x plus p minus 1 into log y, log b is equal to log x plus q minus 1 into log y, log c is equal to log x minus plus r minus 1 into log y. Now the vectors will be perpendicular if the dot product is 0. So we write the dot product here, which is q minus r into log a plus r minus p into log b plus p minus q into log c is equal to 0. Once we have this equation, we substitute the value of log a, log b, log c from here, and you solve this equation and you'll find out that it is 0. So with this, we come to the end of sixth set of problems on AP, GP, and HP. In my next video, I'll solve 10 more problems. And if you have found this video useful and informative, please subscribe to the channel and like the video, because that motivates me to make more such videos. Also, if you have to say something, or you want videos on certain topics, or if you have comments or suggestions for improvement, leave me a comment in the comment box below. And as always, enjoy.